Hey, and welcome back to Graph Theory. We're going to, in this video lecture, wrap up our work in section 5.1 on Eulerian circuits and trails. You got the goals for this video lecture in front of you there. Really, the first one is primarily the main goal. I want to state and prove a characterization of Eulerian multigraphs. So give you an if and only if condition when a graph would have an Eulerian circuit. All right, and after we give that proof, we'll define a sort of related, slightly weaker notion of semi-Larian graphs, multigraphs, and then we'll state, but not prove, a characterization of those things. Maybe we can do the proof in the online Zoom meeting class if you can make it. Okay, so this theorem, it's a slightly stronger theorem than what is stated in your book as theorem 5.1. In your book, I'm just going to kind of draw a little picture here. Your book states this theorem for connected graphs, multigraphs G, excuse me. My theorem allows for G to have a bunch of vertices. It can have more than one connected component, but only one of the connected components is non-trivial in the sense that it can have edges, okay? So it's a slightly more general theorem in the sense that it allows for these sort of stranded things, but in some sense it doesn't really make the theorem much more interesting than 5.1, because if you're finding an Eulerian circuit in a graph like this, well, these vertices that have no edges on them are never going to be traversed to because, well, there's no edges to them. But anyway, that's the theorem I'm going to prove. So let's take a look at the statement of it. Okay, so the statement is that you have a multigraph G, and I'm going to try to prove to you that it has an Eulerian circuit if and only if it has at most one non-trivial component. So there's at most one component that has edges in it, and all of the vertices have even degree. All right, so you have some graph G that looks like this, and all of the vertices that are in the non-trivial component, they all have even degree. If that's true, then it's Eulerian, and if it's Eulerian, then that's true. That's what we're out to prove. The first half of the theorem we've talked about was given that they gave this proof on the first day of our graph theory course. It was given by Euler to settle the Königsberg bridge problem. So let's just kind of rip through it here again real quick. So take a multigraph, and let's suppose that it has an Eulerian circuit. We'll call the circuit C. Okay, so we've got some graph, and it's possible, starting at some vertex, to traverse every edge in this graph once, return to that same vertex, and I'm calling that circuit C. So every time you come to a vertex, I'm saying each passage of C through a vertex, you use two edges, one that you come into the vertex with and one that you leave the vertex with. So you can pair the edges. I'm also going to pair the initial edge and the terminal edge, that beginning and end vertex. You leave it at the beginning, you return to it at the end, so they pair. So all of the edges in this graph pair up, right? So every time, at every vertex, every time you come into a vertex, you have to leave it, even including the beginning one. You just left it first and then came into it at the end. So if you can pair up the edges at every vertex, then every vertex has even degree. That's it. As far as these other conditions, two edges could be in the same circuit if and only if they're in the same component, right? Because if you can traverse along these things on the same circuit, then in particular, you're in the same component. So G can't have more than one component that has edges in it. Otherwise, this circuit wouldn't exist. Every edge is on the circuit, so they're all in the same component. So if G has other components, they look like this. They're just dots around this Eulerian graph. Okay, so that's the direction of the proof that was proved by Euler. I'm going to give a slightly, I think, more rigorous proof than what the author does in your book, although I won't call your author's proof non-rigorous, but I'm going to prove the converse. I'm going to prove that if you take a graph with at most one non-trivial connected component in which every vertex has even degree, that graph has to have an Eulerian circuit, and I'm going to prove it by induction on the size of the graph. Okay? So I'm going to try to be a little bit formal here and start by stating what set I'm inducting on. So let me define a set S of non-negative integers. So S is a set of m's that are greater than or equal to 0. It's implicit in the notation, but just in case, let me emphasize it that m is an integer. And what is this set S? This set S is the set of non-negative integers that have the property that whenever you take a multigraph of size m that has at most one component that's non-trivial, and the degree of all the vertices in that graph are even, then that graph is Eulerian, all right? So if you like, you could say that this set S is the set of M for which multigraphs of size M are theorem holds. That when they satisfy this condition, that they have at most one component that's non-trivial and all the vertices are even degree, then they're Eulerian. Okay, so I'm going to try to show you that that set S is actually the set of all non-negative integers, and I'm going to try to do that by induction. So an induction proof starts by showing that there's some element of your set S. So I'm going to start with 0. All right, so suppose that I have a multigraph of size 0. So it has absolutely no edges at all. So it's a graph that looks like this, if you like, if it has order 4. It has no edges whatsoever. Notice that it has at most one component that's not trivial. All of its components are trivial. And so if you want an Eulerian cycle in that, I'm just going to kind of say it vacuously. Take any closed trail on any one of the vertices. So what does that mean? It means pick a vertex and stay there. And vacuously, that satisfies our definition of Eulerian cycle. So that shows that the number 0 is an S. Okay, so now let's suppose that you have some number that's at least 0, and it belongs to S. Excuse me, that's not what I mean. I am going to be using strong induction. So let me fix this on the fly. It's too late to restart this video, and I don't know how to edit videos, so I'm going to just fix my error. I'm going to suppose that m is some integer that's greater than or equal to 0, and all the numbers 1, 2, up to m all belong to S. I'm going to be using strong induction, all right? So suppose that all of the numbers between, excuse me once again, 0, come on, Tyler. 0, 1, and so on up to m, they all belong to S. So that's my, if you like, my induction hypothesis. Okay, so all of the graphs. And now how do I show that the set S is inductive? Well, I have to take a graph that has size m plus 1, and let's suppose that it has at most one non-trivial component and that all of its vertices are even degree. And what my job is to show you that that graph has an Eulerian circuit, because then I can conclude that m plus 1 belongs to my set S, and then I can conclude that S is all non-negative integers by the principle of induction. All right, so that's what we're going to get down to here. So we've got this graph. It has m plus 1 edges. Its size is m plus 1. Well, then it must have exactly one non-trivial component. It doesn't have just at most one, it has exactly one, because it has some edges. So again, if it had more than, well, I'm assuming that it has at most one non-trivial component, and since it must have at least one edge, it can't have all trivial components. Sorry, that came out kind of badly, but it must have exactly one non-trivial component. It must look like my little schematic picture, that it's got this component, and then it's got some vertices maybe, but they're all edgeless. Okay, so every vertex in that component has degree at least 2, because the degrees are not 0 because they're in the component, and everything has even degrees, so it must be at least 2. So the lemma from the last time, the lemma from the last lecture says that this graph has a cycle. That cycle actually has to live inside of this component, this non-trivial component. It has a cycle. I'm going to call it C. And now it's going to start sounding familiar to what we did last time in that example. I'm going to define a new graph by pulling the edges on, sorry, another typo, pulling the edges out of the cycle C out of G. Okay, so I just removed the edges from the cycle. And I want to note that that cycle had some edges. So this new graph, G prime, its size is smaller than M. We removed at least 3 edges, actually, from G. So its size is smaller than M. Okay, C was a cycle. So when we removed its edges, every vertex in G either lost 0 or 2 edges. 0 if the vertex wasn't on the cycle C, 2 edges if it was. So in this new graph, every vertex also has even degree, because we've taken a bunch of even numbers and we've reduced them by 2, or we didn't change them at all, and that produces even numbers, okay? So the components of G prime are connected by definition, and the size of each one of them is less than m. So it's an element of S. Remember, we're assuming that all of the numbers from 0 to m belong to S. So every one of those components in G prime has a size that is in an element of S. And those components in G prime also have even degree vertices, and they're components, so they're connected, so they have at most one non-trivial component. They all have exactly one component. So all of that is a long-winded way of saying that every one of those components of G prime satisfies the induction hypothesis. So they all have Eulerian circuits. Every component of G prime has one of these Larian circuits. That's the induction part, the hypothesis. Okay, so now pick any vertex on our cycle C and start, quote unquote, traversing it. Start moving along the cycle along its edges. Right, so pick a vertex, pick one of the edges, and start traversing the cycle. As you come vertex by vertex, always ask yourself, are you moving into a new component of G prime, a component that you've never been to before? If the answer is yes, when you enter a new component of G prime, that is, you reach a vertex that's in a component of G prime that you haven't been at before, that component has an Eulerian circuit, so traverse it. Traverse that circuit, returning to the vertex that you came to on your cycle. Okay, and then you just proceed that way. You proceed all the way around your cycle. So since every edge in this graph, this multigraph G, is either in one of those components of G prime or it was on the cycle C, when we're done with this process, we will have traversed every edge in the graph G, and we won't have, or multigraph G, and we wouldn't have traversed any edge more than once. All of the edges and the components of G prime were once because of those Eulerian circuits, and we traversed the cycle C one time around. So basically, we've produced an Eulerian circuit in G. That means that the number m plus 1 is also in S, and so by the principle of mathematical induction, S is the set of all non-negative integers. All right, so that's what proves our theorem. Okay, you can stop that, slow me down, go back, watch it again, but that's my best shot at giving an argument for that. Let me just point out that the author's book, the author of our book's theorem 5.1 is this theorem for a connected multigraph. All right, so that's the actual statement of theorem 5.1, that a connected multigraph is Eulerian if and only if every vertex has even degree. The sufficient proof is the same. It's the proof that Euler gave, that if you have an Eulerian circuit, then every vertex is going to have even degree because you could pair up edges at each vertex. To convince you that the theorem we just proved proves this theorem, well, if G is connected, right? I mean, we've already proved our theorem above. If G is connected, then it has exactly one component. So in particular, it has at most one non-trivial component. It has exactly one. So connected graphs fall into our, all right. So there you go. There's Euler's characterization of Eulerian graphs. If you're looking at a multigraph, if it's possible, if you can just visually see that every vertex has even degree, then that graph is going to have a circuit. As Isaac said during our meeting yesterday, the proof of this theorem is actually constructive in the sense that if you follow the recipe in the theorem, you can actually produce the circuit. Yeah, pull out a cycle, pull out as big of a cycle as you can if you want to try to make it easy, and then on each one of the subcomponents that are left, find yourself an Eulerian circuit. You could even pull cycles out of them to do that if the graph was unwieldy. All right, cool. Okay, so let's continue on here with a little bit more language, some more lingo. I'm writing kind of colloquially there. So not all graphs are going to be Eulerian. They're not all going to have vertices of even degree, but there's sort of a next best thing. So kind of the analog of an Eulerian circuit would be an Eulerian trail. So what's an Eulerian trail? Well, it also traverses every edge in the multigraph exactly once, but it doesn't have to begin and end at the same vertex. It can begin and end at different vertices. So it's not a circuit, but it's a trail. And people call multigraphs semi-Eulerian if they have one of these Eulerian trails, but they don't have an Eulerian circuit, okay? So I won't call you semi-Eulerian if you actually had an Eulerian circuit, then I'd call you Eulerian. So you're semi-Eulerian if you have one of these trails, but not one of the circuits. The kind of lump it all together adjective is traversable. So a graph is traversable if it's either Eulerian or semi-Eulerian. All right, so you can move around hitting every edge in this graph, either beginning and ending in the same place, that's the Eulerian case, or beginning and ending in two different places, that's the semi-Eulerian case. All right. We won't give this proof here. I'm going to keep this video kind of short, and we can kind of I think we can give the proof. It'll be tomorrow. I'm recording this on April 7th, so the next time we meet will be Wednesday, April 8th. And we can talk about this. The author gives kind of a nice argument for it, but let's just look at the statement. So what does the statement say? So it characterizes semi-Eulerian graphs. So it's telling us when they're semi-Eulerian. And here I'm just going like the author with the connected version. We could talk about graphs that have at most one non-trivial component. So in other words, you can always take this connected version of this theorem and say, well, if your graph had a bunch of isolated vertices, then it would work too. So I'm just trying to kind of tell you the whole story, but it doesn't really make it that much more interesting. Okay, so what does it say? You have a connected multigraph. It's semi-Eulerian if and only if exactly two of its vertices have odd degree. Okay, so you have to have exactly two vertices of odd degree in this thing, and then you can find yourself an Eulerian trail. And conversely, if you can find an Eulerian trail, you must have a connected graph in which all of the vertices have even degree except for two of them. And moreover, in that case, any Eulerian trail starts at one of the vertices with odd degree and it has to end at the other. Yeah? So if you show me a multigraph and it has three or more vertices of odd degree, there's no Eulerian trail in that graph. Maybe you remember the Königsberg graph. We've thought about it quite a bit in here, so we can kind of remember what it looks like. The Königsberg bridge problem graph looked like this. So in looking at that graph, I can see a vertex of odd order. I can see another one, but unfortunately I can see more. In fact, I think all of those vertices have odd order. So this graph is not traversable. This graph cannot have an Eulerian circuit. It cannot have an Eulerian trail. It's not traversable. Okay, I'm going to call this lecture there. I hope you can look at it before our class meeting on April 8th, but if not, we can try to hit the high points in that class meeting, do a couple more examples, and then we'll be all teed up for Friday, the April 10th, where we'll take a look at a related notion called Hamiltonian graphs. All right, thanks for listening.